So here's a summary of what we'll be covering in this project. We'll start with a brief introduction to the inverse design method. Then we'll be looking at how the mean-line design of a small-scale heat pump compressor stage can be performed. Then we'll see how the impeller can be designed using the 3D inverse design approach. And then we'll evaluate the aerodynamic performance of the impeller based on a CFD analysis. Then we'll see how the performance of the baseline impeller can be enhanced while ensuring structural integrity through the use of automatic optimization with inverse design. And finally, we'll wrap up with some concluding remarks. So let's start with an introduction to the idea behind the inverse design approach, which we use throughout this project. And as you can see in this workflow, these are the inputs that are used by the inverse design method to give us the final blade design. So apart from some basic parameters, these blade loading inputs are really flow related. And so once you have a good understanding of your specific flow issue, whether it's profile loss, secondary flow, or tip leakage that you are dealing with, it's possible to come up with guidelines on the optimum blade loading to tackle each of these issues. And actually this know-how has generality, which makes it suitable for all your compressor applications. And so what's interesting is that you only need to rely on your knowledge of flow physics, and then this method will work for you regardless of your compressor size or which speed regime it falls under. And so this makes the entire process very intuitive and removes any empiricism that's commonly seen in conventional design methods. Now let's look at the design of compressors in a bit more detail. So across the specific speed range, compressors are subject to various flow phenomena and loss mechanisms which are dominant in that particular range. For example, as you can see in this specific speed chart, leakage and secondary flow effects are more dominant in lower ranges, whereas shocks and profile losses take priority in the higher ranges. And in fact, with inverse design, it's possible to come up with a set of optimal design guidelines based on these fluid dynamic considerations of reducing the dominant flow losses for your compressor. And this is actually what we aim to explore through this project. However, when it comes to small-scale, high-speed compressors, there is usually a trade-off between the aerodynamic and structural aspects of the impeller. And this brings us to our problem statement. Now, in case of small-scale high-speed turbo compressors for heat pump applications, the impeller size can be extremely small, even less than 20 millimeters, which results in a large tip gap relative to the blade height, and also requires very high operational speeds to generate the desired pressure rise, which in turn can also have serious implications on the blade stress. And also, while forloading the impeller at the tip is good to suppress the profile loss and secondary flows, it can significantly increase the tip leakage effects. And that's why conventional methods often involve large numbers of CFD and FEA runs in order to ensure that the appropriate trade-off is achieved, which of course consumes a lot of computational time and resources. And so the question then is whether it's possible to come up with a rapid optimization methodology focused at suppressing the dominant losses, but without adversely impacting the stresses in your small-scale turbo compressor. And this is what we aim to explore through this project.